Welcome to your Week 2 guidance on systems of equations and inequalities. The first thing we need to talk about is what exactly is a system of equations. A system of equations is two or more equations solved at the same time. What we're going to do is mostly stick to two equations for right now, but it can be any number of equations. And you want to find the point that makes both or all of your equations true at the same time. So what value of x and y can I plug into my equations and pop out a correct equation? Here's some examples. So here's an example of a system of equations. So the first one is y equals 2x minus 1. That's a minus sign there. I apologize for that. And then an x plus y equals 2. Now, these two equations, when they're put together, become a system. So we want to find the value of x and y that when we plug them into both of the equations, we get a true statement. There's three ways to solve a system of equations. The first one is by graphing the 2 points, the 2 lines. So let's graph these 2 lines here. We can graph using the slope and the y-intercept, or we can graph using the x and the y-intercept. For the first equation, I'm going to use the slope and the y-intercept. Notice in my equation here that my m is 2 and my b is negative 1. That tells me that if I want to graph this equation, I'm going to start on the y-axis where my y-intercept is negative 1, and I'm going to make a dot. And then my slope is 2 over 1, so I'm going to go up 2 and over 1. And I'm going to do that a couple times to help me make a nice straight line. When I connect those dots, I get the line of the equation y equals 2x minus 1. Now let's do the other one. This one is x plus y equals 2. I'm going to graph this one using the x and y intercepts. To find the x-intercept, I'm going to make my y equal to 0, because all x-intercepts have a y equal to 0. So when y is equal to 0, x is equal to 2. So I'm going to graph the point 2, 0. To find my y-intercept, I'm going to set x equal to 0, and I get y equals 2. So I'm going to graph the point x is 0, y is 2. And I can connect those 2 points to make my second line. Now, the solution to the system, remember, is the point that makes both equations true. So it's the point that's going to be on both equations, or the point where they intersect. So the solution to this system is the point 1, 1. And you can go back and plug them into your original equations to make sure that you got them right. So 1 is equal to 2 times 1 minus 1. 2 times 1 is 1, 1 minus 1, 2 times 1 is 2, minus 1 is 1, so that one works. And then 1 plus 1 equals 2, and that one's certainly true. So you know that you got the right answer. So another method of solving systems of equations is called substitution. Substitution happens when you take one of the variables and substitute it in for the other. The first thing you want to do when solving by substitution is get one variable by itself. Doesn't matter which one, just get it by itself. In this case, we already have one by itself, this y right here. So we don't really have to do the first step. If y wasn't already by itself, you could make it by itself by moving everything to the other side. Now, since y is by itself, we know that y is equal to 2x minus 1. And it's always equal to 2x minus 1. It has to equal 2x minus 1 even in the second equation. So I can substitute 2x minus 1 into my second equation here. Notice I brought down the 2 and the x, but I changed the y to 2x minus 1. Now, the reason we do this is because we now have an equation with only one variable that we can solve for. 3x minus 1 equals 2. Add 1 to both sides, and we get 3x equals 3. Divide by 3, and we get x equals 1. So we've now solved for one of the two variables. To find the other one, go back to that step where you got something by itself. We know that y is equal to 2x minus 1, and now we know that x is equal to 1. So by substituting 1 in for x, we can say that y equals 2 minus 1, which is 1. So the solution to my system is 1, 1. Same problem as the last one, same answer as the last one, so we know this one was right, but if we want to double check, we can always go back and plug it in. The last method is called linear combination, and this is when you combine the two lines together to get rid of one of the variables. First thing you want to do in this method is get both equations into standard form. The way we do that is to make sure we have x, then y, then the constant. This bottom one is already in standard form, so I'll start with that. To put the top one into standard form, I need to move the 2x to the other side. So I'm going to subtract 2x from both sides. And I get negative 2x plus y equals negative 1. Now, we want to combine the two lines together, but before we do that, we want to make sure one of our variables goes away. The way we do that is to make sure the coefficients of one of the variables will match, except for opposite signs. So what I mean by that is if I could find a way to put a 2 right there, then that 2x and the negative 2x would cancel each other out when I added the lines. The only problem with that is I can't just randomly put a 2 in there. What I can do is I can multiply the whole line by 2. Because if I multiply 2 on both sides, I'm not changing the value of the line, just the way it looks. So I get 2x plus 2y equals 4. And the bottom line stays the same. And now I can combine my lines together. So I'm going to add these two lines together. The 2x and the negative 2x cancel, which is what we wanted to do. That's your goal, so always make sure that happens. The 2y plus the y gets me 3y, and the 4 plus negative 1 gets me 3. Divide both sides by 3, and you get y equal to 1. So now we have one variable. We need the other one. So you can go back to either of your two equations, doesn't matter which one, and plug in 1 for y. Solve for your remaining variable, and you see that your solution is 1, 1. So far, all of our examples, well really the same example, was what we call a consistent and independent event. We have two lines that cross at one point, which is the solution, the one point that's on both the lines. Most of our problems are going to have exactly one solution. However, there are two special cases that we need to think about. If you have two lines that are actually the same line, the blue and the green line in this example here, then they cross in a lot of places, infinite places actually. So there's a point right here that's on both lines, there's a point right here that's on both lines, there's a point right here that's on both lines, infinite points. So if you find that you have two lines that are the same line, you have infinitely many solutions. The ways to tell that are that the two equations when put in the same form, are exactly the same. So you get y equals 2x plus 1, y equals 2x plus 1. Or if you're doing substitution or linear combination, you'll find that things will cancel out and you'll end up with something that's always true, like 3 equals 3. If you see something like that, you know that you have infinitely many solutions. The other special case happens when you have two lines that never intersect. They never cross anywhere, so they have no points in common. There's no x and y that make both equations true. This happens when you have parallel lines, as seen here. They never cross, so there's no solution that works. You can recognize this by seeing that the two lines have the same slope. So if you get y equals 2x plus 1 and y equals 2x minus 2. Same slope, different y-intercepts, they're parallel lines. When you're doing linear combination or substitution, you'll see something like 0 equals 4. Well, 0 doesn't equal 4, that's not true, so that would mean you have no solution. The next section that we're going to talk about has to do with inequalities. You did inequalities already in your Introductory to Algebra course, but now we're going to start talking about some more advanced ones. The first type is compound inequalities. Compound inequalities are when you have more than one inequality used at the same time. Here we're going to talk about compound inequalities that use the word and. The word and in an inequality implies that both inequalities have to be true. Another word for this kind of compound inequality is an intersection. Examples of this are x is greater than or equal to -1 and x is less than 4. You're looking for all of the values of x that are bigger than 1 and smaller than -4. So if you think about that, it's all of the numbers that start at -1 and go up to 4. All of the numbers in that section right there. For notation purposes, when we have a greater than or equal to, remember that's inclusive. That means x could actually be -1. So we're going to use a bracket to indicate that it can be -1. X can't be 4. It can be any number up to 4, so it can be 3.99999, but it can't be 4, so we're going to use a rounded one for that. So all of the values between that -1 and 4 would make x true in both of these cases. In the second one, x is greater than 3. So look here, we're talking about all the numbers bigger than 3. And x is less than -2. So what happens there? Remember, the word and means that both inequalities have to be true. Where's the place where both of them are true? There isn't. X can't be a number bigger than 3 and also a number smaller than -2, so this problem is actually no solution. You can also have a compound inequality using or. Or's inequality implies that only one of them has to be true. As long as one statement is true, it works. We also call this the union. So let's think about these examples here. X is greater than 3, or x is less than -2. Now, because it's the word or, we can imply that as long as it's one or the other, it's going to work. So 4 would work and 5 would work because it makes the first one true. -3 and -4 would work because it makes the second one true. As long as one of them is true, we're good. So remember, we need to put in our parentheses here to show that those endpoints are not inclusive. And you're all set. Now in the next example, it says x is greater than -1. Or x is less than 4. Now remember, only one of them has to be true. The numbers down here all work because they make the second one true. The numbers up there all work because they make the first one true. The numbers in the middle all work because they make both of them true. So this problem is actually all real numbers. Every number that exists is either greater than or equal to -1 or less than 4. If you remember back to our AND problem, we had x is greater than or equal to -1 and x is less than 4. There's notation we can use to simplify that a little bit. When we call it the between notation, it basically says that this x falls in between the -1 and the 4. Notice there's always less than signs or less than and equal to signs. It's never greater than. And you go from smallest to largest. When you see this notation, just know that that means that x falls in between -1 and 4. When you solve inequalities, you're going to solve them the same way you would a regular equation. The only difference is that if you multiply or divide by a negative, you need to flip the inequality sign. So here's an example. I'm going to start by solving this first half. 5 minus 7x is greater than or equal to 12. Remember, we're getting x by itself, so we're going to start by subtracting 5. And then dividing by -7. Now remember the rule I just said, if you multiply or divide by a negative, you need to flip the inequality sign. So I'm going to have x is less than or equal to -1. Or, add the 2 to both sides. We get 3x is less than 9. Divide by 3. X is less than 3. So, we have a problem here. X can be less than -1. Or x can be less than 3. Now watch what happens here. I start at 3 with my brackets, and I go this way, and I meet up with that -1. All of the numbers smaller than -1 are also smaller than 3. So this part here is actually dominant. That x is less than or equal to -1 is not really important in this problem because it's an or. The x is less than or equal to -1 kind of falls into that x is less than 3. So really you just need that second one in this case. So let's try an example with the between notation. Same idea, except for now this time instead of having 2 sides where we have to do something on both sides, we really have 3 sides. So to get that x by itself, I'm going to add 3, but I need to add that on all 3 sides of the inequality. So I get 1 less than or equal to 2x less than 10. Now I can divide all 3 sides by 2. So I get 1/2 is less than or equal to x is less than 5. When I graph that, because this is between notation, I know that x is all of the numbers between 1/2 and 5. So all of those numbers in there. The last topic is graphing in 2 variables. What we're going to do here is we're going to combine graphing lines with what we know about inequalities. So, the first thing I want to do is graph the line y is greater than x minus 3. First thing to keep in mind is that the greater than changes the way we're going to draw the line. We're going to make a dotted line to remind us that 3 or the x minus 3 is not inclusive. It's going to be everything to one side of the line, but it's not going to actually be the line. So we start at -3, make a dot. We go down up 1 over 1 a couple times. And you get a line that looks something like that. Now we want all of the numbers that are bigger than that. So that's y equals x minus 3. We want all the numbers that are bigger than x minus 3. So you're either going to shade the right side or the left side, or the top and the bottom, depending on how you're looking at it. If you're not sure, you can always plug in a point. So I'm going to plug in 0, 0. When I plug that into my formula, 0 is greater than 0 minus 3. I get the statement 0 is greater than negative 3. That's true. So that's the side of the equation I'm going to shade. So I'm going to shade everything on that side of the line. And those are all of the values, the x and the y's, that if I plugged into that first equation, I would get a true statement. Now I'm going to do the same thing for the second one. Now I'm going to graph my second one. I'm going to change this because I don't think I meant it to be a 21, to be y is less than negative 1/2 x plus 2. When I graph that, I start at 2. So I'm going to start at 2. I'm going to go down 1 over 2. And I'm going to make a line. Notice again it should be dotted because it's no equal bar there. And I want all of the numbers that are less than that. So again, if I plug in my 0, 0, I get 0 is less than negative 1/2 times 0 plus 2. 0 is in fact less than 2. So all of the points on the 0, 0 side of the line make that equation true. So this looks kind of messy, but what does this mean? Remember, I want and. So I want the place where both of those equations are true. So I'm actually looking for the section where they overlap, which is right here. And that whole section, any point in that section, if I plug it into both of those equations, I will get a true statement. So that's my weekly guidance for this week. Please get started on your homework. See you next week.